this is the truly origin of thermodynamics in a way. And let us say I always call this is thermodynamic template. Every substance which we can say we know the substance if and only if you develop this preliminary template. Without developing this template, you can't say that I know about this substance. One substance which naturally available, sorry, naturally available, and what are the two axes? One is the pressure axis, the other is the temperature axis. And it is good that because of the Lord Kelvin and Torricelli, we got two absolute truths about this particular template. The Torricelli proved that there is a zero absolute pressure below which there is nothing negative. The great Kelvin proved that there is a zero absolute temperature, there is nothing above. Means what does it mean? My entire knowledge about the substance is only in this direction. Okay, so this is called a quarter infinite domain in which you need to define the substance. Okay, so can you give me eraser for this? Eraser. I want to erase this. Erase this one. Erase. Oh. Yeah. Yeah. Mm. Okay. This is what I was explaining you in the class. Okay. You will understand on the template now the origin of thermodynamics also. Pen please. This is the pen. Okay. Now this is the one I started. Nobody could achieve this absolute zero. The lowest temperature achieved so far is 4.4 Kelvin using a liquid helium. But however, this is the first knowledge. On this side, this is a solid. On, on this side, this is a solid. Okay, and this side is vapor. So very low temperature and pressure, only two phases are possible. That is the solid and vapor which I discussed. But this was not very attractive till very long time. People did not notice this one. And afterwards they find what is called a triple point, where there are three phases coming. Okay. So this is called a entire domain is solid domain. And there is a liquid domain. And this entire thing is called the solid domain. This entire thing is called the vapor domain. This entire semi-infinite thing is called a domain. And the actual research started everybody, because the water was available. The people had a water naturally as a liquid, because at ambient pressure and temperature water remains as a liquid. So triple point is such that at the NTP it is a liquid. So this attracted everybody to develop a new knowledge, and that's how thermodynamics created. The change of phase of liquid to vapor is the origin of the entire thermodynamics. And the first time the whole world thought that they produced a new science. The first scientific theory is understanding the water characteristics, which I was starting last class. Go to the slides, please. This is what is called a theory of producing steam. Perhaps all the youngsters, it looks like very obvious. There is nothing very great about it, because you were forced this knowledge without understanding, but it took a few million years to come up with this knowledge. The water and steam are typically used as a heat carriers in the heating system. That's how the knowledge started. The people used this as a heat carrier. But as a heat carrier, they said first knowledge is water boils at 100 degrees Celsius under atmospheric pressure. This was the first truth, a scientific truth which was exciting. So whenever I want to create a temperature of 100, so easy. You boil the water and you have an ample water in your system, and it will go on boiling, 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 and as long as there is a water within your control volume or a control mass, 100 will be maintained. Now, the maintenance of 100 became so cheap, so easy. But what was the challenging is, what about any other temperature? Can I keep exactly 150 for some time or a long time? And then only the substance available easily was water, because they never thought that changing a substance is an option. But later they could produce this particular one at a higher pressure. Somehow you create a higher pressure in your control mass or a control volume. All of you know, if you have a cooker, the moment you put the weight, you can increase the pressure inside because you put a weight. Suppose let us say if I go on increasing the weight of the visual, automatically the pressure inside will vary, and accordingly I will get a constant temperature at which the food will be subjected to for a some time. That's how if I increase the pressure 10 times, I can get a 179.9 degrees Celsius. And 10 times increase in pressure is not even doubling the boiling point. This is very interesting point to be noted. And people went to 100 times the then 10 megapascals means 100 times the normal pressure or atmospheric pressure. So when the pressure is increased 100 times literally, the temperature is increasing only 3 times, 301.1 degrees Celsius. So they have seen a sluggishness increase in the boiling point. Is it a good or a bad is a big deal. The people wanted to understand what are the consequences of this one. A high increase in pressure is producing a small increase in boiling point. Is it the problem with the water? Or is it the nature of all the working fluids will have that kind of a behavior? Means it opened curtains to the new knowledge, new products, anything you say. I still believe that this is the wonderful knowledge. If you go to the stream tables, you will see now with respect to the water, this is all corresponding to a water, a saturated liquid water, saturated vapor. So when all the water becomes liquid, suppose if I take a 1 kg of water in a vessel and I supply the heat such that all the liquid becomes all the water. Okay, this is where. If the pressure is 1 bar, at 100 degrees centigrade first time the temperature rise will not be there, volume rises. You imagine when I wait for the entire volume to be converted into, see, entire mass of water, a liquid to vapor, you see 160, 1670 times the volume is increasing, massive increase in volume. Now the question is, should I be happy? Such a high increase in volume? What are the consequences of such a high increase in volume? It took long time to understand, and it is the Thomas Savery who started exploiting this one, as I showed you in the beginning. And similarly, if I increase the pressure nearly double, 1.985, you see this one, the megapascals is 0.1985 means 1.998 times the atmospheric, nearly double. Then the 20 degrees Celsius rise, and you see this one, the vapor volume drastically decreasing. Can you see very funniest thing? When I double the pressure, the change in temperature or a boiling point is only 20 degrees centigrade. And the change in specific volume of the liquid is almost negligible, 0.00104, 0.00106, hardly anything. But on the other hand, when I come to the saturated vapor volume, it's half, nearly. Why this fellow is so proportional to the pressure? Is it a good behavior? And how do I exploit is the state of the art. It looks like the vapor responds to change in pressure a lot. If that is so, I can do wonders, and I can construct what is called artificial animals and replacing all the animals for the mechanical power production. And you see this one, when it becomes a 5 times, you see 0.475 means nearly 5 times. Now you see 1.6 by 0.4. So if you see the pressure ratio and volume ratio, they're almost same of the saturated vapor. Whereas the liquid hardly responding, you see, liquid volume doesn't respond, that's why it is called incompressible fluid. It doesn't respond to the pressure, whereas saturation temperature is marginally responding, and whereas specific volume of the vapor is responding proportionally. Can you believe same substance and three different characteristics behaving differently? One specific volume doesn't respond, the boiling point responds sluggish way, and the saturated vapor volume responding proportionally, and led to the great thinkers like a Boyle, Charles. What is this? How do I connect? What is the correspondence between these two? Is the greatest science, and led to the thermophysics. One of the ancient branch of the physics or a formal physics is obviously thermophysics. You can see this one 200, 250, 500, and you can see this particular one 0.1 to 8.58 means 85 times. When I increase the pressure somehow, you can see the correspondingly 1.67 by 0.02, nearly 85 or so. You are getting a proportional changes, and this attracted the people. This made the Boyle and Charles to do some wonderful experiments, and this Thomas Savery's invention demanded a science to construct also, okay, which led to good pace in the scientific knowledge. And the people wanted to understand what is between these two. Okay, this is the saturated liquid, this is the saturated vapor. Suppose, is it possible to have somewhere in between, or it is a sudden jump? This was another interesting point people wanted to know, and this knowledge led to what is called a concept of wet vapor. What is the meaning of wet vapor? There is some steam, but there is some amount of water also. Isn't it thrilling? I have some drops of water in the steam, or I have a few bubbles of steam in the water. Both the things are exciting for a researcher, and wet vapor is a mixture of steam and water and at the same temperature and pressure. Now the question was, the initial thinkers and genius people wanted to understand this one. If I have a mixture of liquid water and vapor water, or a steam, or a water and steam, and who will decide whether steam should be like bubbles and water is the medium, or what will decide there is a steam flow inside which all the water is like a droplets? You imagine both are a mixture of liquid and water. Now I want to wonder whether in the water media steam will be bubbles, or in the liquid media, sorry, in the steam media water will be droplets. Who decides? You see, even today this is one of the wonderful knowledge people use a hi-fi techniques to understand this one. The saturation pressure is the pressure at which liquid and vapor phases are in equilibrium. So every pressure now, for every substance there is a pressure at which two phases can be produced. Means by having a peculiar combination of temperature and pressure, you will get one combination. Any arbitrary pressure and temperature cannot give this one. There is a specific combination which can provide both the things together. Otherwise, either you get a only liquid or a only vapor. But if you want a mixture, no, you need to be very careful about a pressure and temperature. That's how the people found a dual, kind of a couple made for each other to create a mixture of these two. One is called a saturation pressure. Okay, for a given temperature, any pressure, there will be a pressure which will give you both existence. And or suppose I can think in the other way, what is called saturation temperature. For a given temperature, if I vary the pressure, I can create a mixture of these two. That's how there is a couple. And depending on what is with you, for a given temperature, you can change the pressure to get the wet vapor, or for a given temperature, you can change the pressure to get the wet vapor mixture. Strictly speaking, saturation pressure and saturation temperature are a couple. There is a perfect relation between these two, and each substance will have a different relation. See the knowledge. For a water, there is a combination of pressure and temperature which can produce both. Otherwise it is impossible. And if I change the substance, the relation changes. At the same pressure, saturation temperature will be different for different substances. What does it mean? How this knowledge will help me? What is the use of changing my substance from water to something else? Do I get extra benefits? And that is where the thinking and innovations will start coming. The saturation pressure is a function of saturation temperature and vice versa. And that's how the people wanted to do this knowledge. What is the relation between the saturation pressure and temperature? Why I want? In this combination, I can have a mixture of steam and vapor. And still know how much vapor, how much is water, is it always 50-50? Or is it always 10-90 or a 90-10? This is another curiosity. Suppose if I get a combination of pressure and temperature, whatever couple, which is trying to produce a mixture of vapor and liquid. Now the next question is, this proportion, will it be always 50-50 independent of anything? Or no, liquid is always 10%, vapor is always 90%. No, vapor is always 10%, liquid cannot be more than 90%. Is there a rule? Now who will decide is the next question. Who will decide what should be the relative proportions? There are two knowledges. When should I get these two? Number one. After getting this one, what should be the percentage? How to control them? Because even the percentage control was essential for a better engineering. I may give example little later. So this is the beautiful thing. The saturation temperature is a function of pressure or vice versa. Pressure is a function of temperature. It's a inversion of a relation y is equal to mx plus c kind of relation, or maybe. So one of the most powerful equation I am not discussing, there is a big history of this one. I am giving you the most authenticated equations which we use a lot in our research, what is called a Wagner-Ambrose equation. And what is the greatness of this particular equation is, you can get a relation between the temperature and pressure for any substance you want reasonably accurately. That's how it is. Not only for water, you can develop for other substances also. Now you see this one, logarithmic of saturation pressure is a very complex function of temperature. What is this tau? You can see this particular one. The tau naught is defined as 1 minus TR corresponding to the saturation condition. What is the TR? This is the one. So people have to find out a new point to get the relation. What is this new point to be invented to get a relation between the saturation pressure and saturation temperature? Very interesting, no? Suppose if I am planning my journey that I should travel via this place, or A to B I will travel on the road, B to C I will go by a train, C to D I will go by aeroplane. All this plan is successful because after all, what is the relation between the pressure and temperature? A route. How can you plan the journey without knowing a destination? So that's how. Can you give me the whiteboard please? Okay. Now you see this one again I compare to. That's why now I call it as a template. This is the template on which entire invention knowledge will occur. So this is the pressure and temperature. This is the absolute zero. And this is the liquid solid sublimation line. The first time there are three phases existing, and this entire domain is solid. This is the liquid, this is the vapor. So what I am looking like is this relation. For every substance I want to have what is the shape of this curve, what is the relation between the pressure and temperature, okay, where liquid and vapor both are possible, because this is the border between the liquid and vapor. If I move along this particular line, both are possible. And what is the percentage? I need to know more. Now the question is, in order to develop this line, you need to know, can this line extend it to infinite? And very funnily, this particular will not extend to the line here at all. There is a destination after which you don't see any difference between the liquid and vapor. What does it mean? If I go on adding the heat above this particular point, if I go on adding the heat, temperature will continuously change. I'll never get such a dilemma which I was getting like temperature increases to up to some percent. and though adding the heat, temperature doesn't change, only volume changes. And if I see for some time, and again volume temperature both changes. You recall last time, a peculiar combination. If it is a liquid, volume doesn't change much, temperature changes a lot whenever I add a heat at a constant pressure. And suddenly there is a point, temperature doesn't change, only volume increases tremendously. Afterwards, again there was another point where volume temperature both change with respect to heat addition, because three different behaviors. All those three different behaviors are possible when you are working below this one. Suppose if you are working above this one and the behaviors are different. So that's how the people wanted to know what is this point after which the liquid doesn't exist at all. This behavior doesn't exist at all. This is what is called a critical point. I'll come back to this one. And without knowing a destination, no, you cannot map your journey. I need to know the journey, destination, what should be the shape. That's how, in order to know, starting point of this one is always triple point. And this journey gets finished. The relation between the pressure and temperature gets finished the moment I go to a critical point and critical temperature. So this is the one which is required to develop the formula on an average. Very fundamental. Most of the textbooks ignore this particular knowledge, which is very bad. In fact, there is no development possible without this relation at all. All the effects of Thomas Avery, Newcomen, James Watt, Rankine, all these products came by understanding this relation. I don't know how many years they worked to get this relation. That is the reason I cannot ignore some knowledge which is very essential for a engineering product or development of engineering product, because this is engineering thermodynamics. The knowledge required to create a product should be studied. And I don't know why many books do not worry about this one. Go back to this. You see this one? It's after all a complex formula. What I am doing, I am trying to know, you see this one? I am trying to know what is the critical temperature. Okay, every saturation temperature I am trying to normalize. Okay, so based on the normalization, I created what is called a temperature ratio, or sometimes some books call it as a reduced temperature. We'll come back to this one later. Very important, this reduced temperature. And he's defining a variable which is 1 minus reduced temperature. So based on this particular one, he got a relation between the pressure and saturation temperature. Very complex relation. Unless he developed that kind of relation, suppose you can substitute everything back, and if you want to know exactly saturation temperature, function of saturation pressure, you substitute this one into this one into this, all these things, you will get a very complicated. Just to represent simply, we are having a 3 levels of this one, and this is the one knowledge which can be used for anything. Okay, so the equation for saturation condition of water, what is called a saturation properties of water. And there are other things. As I said it now, the people were not comfortable with such a complex formula. The people wanted to have a straightforward formula. This is the straightforward, much simpler than this. But this particular formula is only valid for the water. And the formula which I have given is valid for anything, but you need to know the constants of those equations. So this is essential knowledge. You believe me or not, without knowing this knowledge, many industries will not work at all. There are many industries which use steam for milk product production, the steam for pharmaceutical, steam for some chemical products, etc. All these are nowadays, the biotechnology is a very boom. Most of the biotechnology based industries use a steam various temperature to develop biotechnology based products, genetically modified products, etc., whatever it is. All of them have to create a temperature, sustain a temperature only by using a water most of the time. So this equation is very essential for developing first level of engineering, you believe me or not. That is the reason why I am saying. So the moment I know what is this particular equation also talking about is the PT relation. So you see this particular one, if I go on to see the same thing now on a TV relation. Okay, you see each one is a constant pressure. You see at this temperature, this is the saturation pressure, and if I increase the saturation pressure, again saturation temperature changes. Again if I increase, you see this one, if I keep the temperature the pressure remains constant, or if I keep the pressure constant, temperature doesn't change, though volume is changing and I may be adding the heat, but that is not possible. If I go on increasing the pressure, the temperature, that constant temperature is the one which we got the relation slowly. Suppose if the same phenomena, if I see in a temperature versus volume diagram, it is saying something beautiful. What is that beautiful? You see the entire interesting point. So if all the saturated liquid states, you see this one, this is called a saturated liquid. Why it is saturated liquid? As I go on heating the liquid, first time the temperature stopped changing and volume started increasing tremendously. Again when I increase the pressure, again the temperature changed. That's how these are the points which are called as saturated liquid lines. Okay. So I am trying to join with a blue curve. Okay, and afterwards there are other points. You see this one, this is the first time again the behavior changing, means what will happen here onwards, both volume and temperature both will change. Before this one, volume can change but not the temperature. When I increase the pressure, this point is changing again. When I increase the further pressure, it looks like the fluid is becoming more sensible very early, isn't it? Suppose if the pressure is very low, for a very long duration or a volume, the temperature doesn't change. Suppose if I increase the pressure, the temperature and volume start changing very early. If I further increase the pressure, such a change occurs early. Now I showed it to you, the behavior of this particular vapor, the volume changes proportional to the pressure. And as I go on doing this one, okay, it is coming early in terms of volume. That is the one which is interesting factor. The people wanted to understand this particular one. So if all the saturated vapors are connected, this is called a saturated vapor line. What is that? I am joining with a red line. You can see this particular one. So every substance has its own dome. It is called a dome, vapor dome. What is the dome? If you take a combination of pressure and volume which is here, this has to be mixture of liquid and vapor or a water and steam. It is impossible a combination of this pressure and temperature being superheated. Okay, so that's how there is a region in which you can have the combinations occurring. If always I keep the entire fluid, whether there may be a heat loss or a heat gain, if I keep the substance within the dome, what will happen? I can maintain a constant temperature by keeping the pressure constant. That's what exactly I was telling you in the last class. I can deliver a hot pizza at a given required temperature without spoiling it by taking a fluid which is in the range. So that's how till I deliver, the pizza will be hot. Or there could be many applications which I was trying to tell. The people wanted this dome, and this is the dome which I am plotting for one fluid. For some other fluid, no, the shape will be something else. Okay, so all the knowledge will lead to many products. So these two lines intersect point called a critical point. Now what is this particular point where they are intersecting? This is the same point which is a destination of this liquid journey. Afterwards, what is happening? There is no such thing at all. If I go on adding the heat, the temperature is continuously increasing. The volume is continuously increasing. Though the pressure is constant, neither the temperature nor the volume remain constant. They continue to change. But however, below this particular line, the volume changes very slowly. Afterwards, volume changes rapidly. Now, I want to know up to what point the change in volume is negligible. After what point the change in volume is considerable. Now my entire knowledge requirement has changed. I want to understand where is the turning point. You see this particular one? If I see this particular line above the critical point, so a large change in temperature is producing a small change in volume, isn't it? It is so steep. What is the meaning of it? Very large change in temperature is essential to have a small change in volume. The moment I cross this border, you see this one, the line is becoming in a way, means its volume is changing much faster than the before. Means still there is a turning point or a cross. But what is the most important is The two lines intersect a critical point and form what is often called a steam dome. There is a closed envelope. Means the existence of this mixture is never for a very infinitely long. Now you imagine in the entire domain of that quarter infinite domain of PT curve, nothing happens at a negative P absolute. There is nothing like a negative temperature absolute. Only the things materials can have a behavior is absolute pressure and temperature supposed to be positive. Within this domain, there are various behaviors. I have shown you that curve because that is the curve which gives the complete picture of material behavior. By understanding this one, you can develop a more and more products. So I am putting a dot. This dot is the one very essential to know because below this dot, above this dot, the behavior changes. In fact, now strictly speaking, this is the end of journey of that liquid to vapor thing. And above this one, no, it is impossible to maintain a constant temperature while having a heat transfer at a constant pressure. Afterwards, no, if I want to have a constant temperature, no, I need to manipulate both the pressure and volume, not can be anything. So this is an inconvenience or a benefit. It is up to the person who is using these benefits. Now you see this one, the critical point of water is 374.14 degrees Celsius and the pressure is 22.09 megapascals, means nearly 220 times the atmospheric pressure. When you increase the pressure of the water 220 times, you make it to 220 times, automatically you will lose that behavior. What is that behavior? A constant temperature corresponding to a pressure. If I go on adding the heat, only volume changes, temperature cannot change. Such a situation disappears. Below this one, there is a peculiar behavior that for some time, for some volume range, there is a behavior. If you wish, you can exploit this. If you are not comfortable for this, you can use this one. Can you believe the great scientists and technocrats and engineers used this knowledge to divide the entire purpose. So suppose if I am using the substance here, I am using the substance as a heat carrier. Alright, this fluid is doing a heating jobs. And suppose if I want to use here, no, this is the best to do what is called a mechanical work generation is more powerful here. We'll learn this particular one. You take more time to understand. Finally, the people wanted to get an equation again for this one, isn't it? I need to know what is the equation of this blue line, what is the equation of this red line. Very important to know. Without knowing this one, I don't know whether this substance is fit for an application or not fit for an application. You believe me or not, ignorance of these relations, the shape of this curve, led to a situation that we misused the steam, we underutilized the fuel, and most of the reasons why solar thermal power is not feasible because the people did not understand this fact. The day when understood, they said that steam is not a good thing if you want to produce power with the solar. If I change the steam with some other working fluid, why and how, let me tell you. Always you should have more knowledge. Again, I am very upset, common thermodynamics books do not talk about that. For every engineer, it is very important to know the shape of that saturated liquid line. For every engineer, it is very important to know what is that saturated vapor line, how these lines are changing, where are they intersecting, why they are intersecting. Exactly that point is essential to develop a more important products. All the books avoid, but a modern technology requires this one. Perhaps somebody has to give. This is the one, the density of the liquid by the density at the critical point. 1 over the density is the specific volume. So you will get the temperature versus curve. How I am substituting the temperature? Same way. So the temperature is non-dimensionalized with the temperature, the tau is, I defined you, the tau is the temperature divided by the critical point temperature. Okay. Similarly, you can have a line for a saturated vapor. This is for water. Okay. I am giving all the constant. Means for a water, no, I can construct the entire dome. Very well in advance, I will understand how the dome is changing. I don't have to do thousands and thousands of experiments again and again to know where exactly this dome disappears, because the people who does experiments once will try to develop this formula. Using this formula, no, I can always develop a new products. So that's how these formula are very essential. Even at a first level now, you should understand that it is possible to get one equation for the saturated vapor line. For every substance there is a separate formula. It is possible to get an equation for the saturated vapor line. That is one. Every substance will have a different formula. Why difference? What is the utility to know the difference is the one modern technology. The day we come to know, no, we are developing a more renewable energy based systems. Okay, so that's how. Let me consolidate this vapor dome. So the region between these two, okay, and this is whatever I said, no, I'm consolidating here. Okay, the region inside the dome I'm talking about, I don't have the lines here, this entire dome I'm talking about. What is the dome? The dome will have a mixture of liquid and vapor, and it is a wet region, okay, because there is wetness of liquid available. Generally it is called a two phases existing together, liquid phase, vapor phase, and all these things will have a more challenges, more products develop. That's how some people say this is called a saturation region. Why saturation region? During this point, whatever you do, the pressure and temperature both remain constant, and if you go outside, you cannot keep the pressure and temperature together. Then you need to play a lot to keep the things constant. The trend of temperature following a constant pressure line is increasing with the increasing volume. Okay, you can see this particular one, the trend of temperature following a constant pressure. You can see this particular one. So if you see this constant pressure trends, okay, and the trend of pressure following a constant temperature line is decreasing with the increasing volume. On this one, you need to know this one. I am not giving a more explanation. On this platform, on this PV diagram, you can see this one. An increasing temperature line following a constant pressure is increasing volume. At a given constant pressure, an increasing temperature is giving more volume. In the same way, at a given temperature, increasing pressure is decreasing the volume. So these are the two innovations done by none other than the Boyle and Charles. You know the Boyle's law. Boyle's law. What is the Boyle's law? P is inversely proportional to volume, or volume is inversely proportional to pressure. What is the Charles law? Volume is directly proportional to temperature. All this knowledge, the first information which is taught to you is a new knowledge. In fact, no, that is the origin of scientific thermodynamics, where people wanted to know. That's how the people wanted to know this wet vapor more closely. Okay, what is the wet vapor and how do you understand the wet vapor becomes very important for a many products. Now the question is, the idea is how to know how much vapor or how much liquid, and how do I classify this particular one. Okay, give me the whiteboard please. New. Okay, so we want to understand this particular one, what is called a wet mixture. Okay, what is the meaning of wet mixture? I can explain in many ways. Suppose if I take a temperature versus volume diagram. Okay, I showed you there exists a dome. Okay, and if I am inside the dome, then I can say I have a vapor mixture. Let us say I am fixing one pressure, automatically temperature remains constant, isn't it? Afterwards, at the same pressure, the temperature decreases like this if I go this way. So this entire thing is, I take a liquid at a constant pressure, if I go on adding the heat, the temperature will increase. And this is what is called a saturation temperature corresponding to a pressure of P. There is a dual. Afterwards, now whatever I do, add heat addition, temperature cannot change, only volume will change. Okay, so this is the first time again there is a change in behavior of the substance for this. So this is called a saturated vapor, liquid, saturated vapor. Suppose if I have a point here, okay, mixture. This is the location. Let us say this is A, the B, and this is the C. Now the question is, at C, okay, there are many doubts. What are the doubts? What I know is both liquid, okay, plus vapor possible. This is the truth. Or water and the steam both are possible if it is a H2O thing. Now the question is, how much? How much water and how much steam or a vapor, liquid vapor or a water steam, that is a forming I am using as a synonym. No question. How much? Will it be a constant or should it be always 0.5, 0.5, 0.5? So this is the one which wanted to be explicitly understood. So that's how the people wanted to see a kind of thing, the fraction of water in a wet mixture. That became very important thing. Or I can know in the other way. What is that one? The fraction of steam or a vapor, whatever way you use it, in a wet mixture. I am using the fraction. So what is the meaning of this fraction? The fraction of water in a wet mixture plus the fraction of steam in a wet mixture should be equal to 1, because after all they are fractions, isn't it? How do I define this particular fraction? Should it be based on the volume or should it be based on the mass? So a lot of discussions went on, and finally people agreed that better to follow this discipline. This is a universal discipline. As I said it now, always thermodynamic understanding is internationally accepted before publishing a book or a paper. So next one please. So that's how the people define a function called x, okay. And what is this function defined? Later we'll give the name to this one. The mass of vapor divided by the total mass of the mixture. Okay. Now what is the meaning of total mass of the mixture? Obviously this will have mass of a fluid. Generally this is the standard for liquid, plus mass of vapor. The F stands for liquid, mass. So this is what is called X. The specifically agreed. Number one, what is internationally agreed to know this particular one is, it should be a mass fraction, not the volume fraction. Okay. And also the definition should be only based on the how much is the mass of vapor by what is the total mass should be the important. And suppose if I want to know mass of liquid out of the total mass of the mixture, this will come automatically, isn't it? What is this one? This will be equal to 1 minus x. Now what is the title given to the x? Now because this is the one, suppose if I take a steam and if there is no liquid at all, assume that I can bear, if I put my hand with the glues etc., I don't get my hand dry, wetting at all. Suppose if there are some droplets or some water within the steam, if I put my hand or if I put any surface into that one, there will be wetting of surface occurring. So that's how the people said that this is phenomenologically correct. When I take a steam beyond a saturated vapor, whatever I keep inside this one, there is no wetting, no liquid is found. Suppose if I have below that one, below saturated volume, if I keep a surface immersed into this one, I'll see beautifully some droplets formed, etc. So that's how the people wanted to name phenomenologically this as wetness. Okay, so because I am giving as a fraction, not as a percentage, if you want, you can give a percentage also, but mostly this is a fraction. Now you see, if 1 minus x is a wetness fraction, what should be x? So obviously dryness fraction. Okay, so the dryness fraction is a measure of the percentage of the amount of mass of vapor in the total mixture. So higher the value of x, more will be the vapor, lesser will be the thing. So that's how you can see this one. If 1 minus x is equal to 0 means all vapor, x is equal to 1. If x is equal to 0, the wetness will be 1, means all the liquid. So literally the x can vary from a scale of 0 to 1. And afterwards there is no meaning of x at all. The definition of x is valid only when you are inside the dome. If you are outside the dome, x has no meaning at all. It is a local definition. Very important. If your state is, let us say I am trying to draw the dome above this particular one. Sorry, this is the one. Okay. Now you see this one. If it is above the dome, sorry. Okay. If I draw the dome, so x has no meaning on this side. X has no meaning on this side. If still somebody counts, x remains to be 0 here, x remains to be 1 here, and x varies from 0 to 1 in this particular range. So that's how the dryness fraction, and most of the book somehow said it because of the engineering consequences, which I will tell you later. The same thing is called sometimes quality. Okay, what is the meaning of quality? If the quality of steam is 1 means all steam, all vapor. If the quality of a given mixture is less than 1 means there is some amount of water. If the quality of the steam or a mixture is 0 means it is a liquid. That liquid could be anything, maybe saturated, maybe unsaturated. If the quality of the steam is 1, maybe saturated, maybe beyond that one also. So that's how the wet mixtures helped a lot to define. The people wanted to know amount of the mixture. Okay, the moment I know this particular mixture, so I can calculate many properties by knowing only at this one or a last point. So that's how the whole industry started using this particular information, and the wet vapor developed a new information. Okay, pressure and temperature are independent or not independent properties. Whenever I have a wet mixture, for every pressure there exists only one temperature. You cannot have independently pressure and temperature varying. That is the first one. The second one is the either P and V or a T and V are independent. If you, by keeping the pressure and temperature same, I can increase the volume. How can I increase? By increasing the dryness, isn't it? As the more and more steam there, automatically volume was increasing. You have seen the domes also. Okay. The maybe P versus specific volume, T versus specific volume can be independent. So a new property is defined for use of steam for a ease of design. Why? They wanted to know what is the fraction of steam. That's how they defined the new property, which I said, quality. This is called quality of the wet steam, or sometimes books call it as a dryness fraction, and which is most popularly used as x, but there is no rule that it should be. The moment x is greater than 0, less than 1, the point should be inside the dome. You can see this one. The point 3 is having an x less than 1, greater than 0. Suppose if I am at a 2 or a below, x is 0. If I am at a point 4 or above, it is 1. So defining quality here or a quality here is stupid. There is no reason at all. But the quality starts with 2, and after 4 quality should not be used at all. And the quality definition I have just given you in the entire thing. And this can be used in many ways in the engineering. Okay. The state 3 is a mixture of saturated liquid and vapor, which I explained to you. And how do we locate the TV diagram? Okay, how do we locate it in the TV diagram? How? I gave you by defining the X. And to establish the location of state 3, the quality X is defined. Okay. How did I define this particular one? This is the one. The mass of saturated vapor divided by the mass of the liquid plus mass of the vapor. Here, sorry, here they are using G for gas and F for liquid, or G for vapor and F for liquid. Each book will have its own, but you need to understand that the dryness fraction is the ratio of the vapor mass to total mass. The total mass contains some liquid mass, some vapor mass. And FVG is a book to book, there could be a variation. Your teacher may follow this one. The quality is 0 for saturated liquid, as I said it, okay. And the average specific volume at any given point 3 is given in terms of quality. Suppose if I want to know what is the volume at this particular point, so easy way of doing this one is, consider a mixture of saturated liquid and vapor, okay. And the liquid has a mass fraction of mf and occupies a volume of vf. And the vapor has a mass of mg and occupies a volume of vg. Okay. So then how do I calculate the volume of wet mixture? What do I have? What is the the first question is, what is the phase transformation? It is very important. This phase transformation word is used in solid to liquid phase changes only. And generally we don't use this point of phase transformation in liquid to vapor phase change. Why it is happening is, suppose when you make the metals and alloys, by changing the composition, now you can get different saturation pressure and temperature combinations. And because of that phase transformation, cooling, etc., I am avoiding this one because I haven't taught so much metallurgy. If I start discussing the liquid to liquid, liquid to solid with the mixture, that becomes a big metallurgy. I want to say precisely that phase transformation word is used when you are talking about alloys, number one, and these alloys cooled from a liquid to solid or heated from solid to liquid. So that's how this particular term I will not elaborate more because it goes more outside. Without teaching that much, I should not talk. The second question is, sorry, yes, at the critical volume, the enthalpy of latent heat is 0. That is true. You are very much correct. The latent heat slowly decreases as you increase the pressure. First time the latent heat becomes 0. What does it mean? What is the meaning of latent heat? You cannot have a heat addition without changing in the temperature. That is meaning of latent heat. So below this point you can have some latent heat without changing temperature. This entropy, I'll discuss later because when I introduce slowly, I'll come to first law, second law. You please question after I introduce the entropy, because if I say now, that will confuse. I'll come back to this one. In fact, I'm more serious about this entropy, material selection based on the entropy, but I think this is not the time to discuss that particular point. Any more questions? No questions, no? Okay. I'll just introduce this point. Can you give me the whiteboard? Okay. Suppose let us take this particular same temperature versus volume diagram. At a constant pressure, if I take a liquid first, the slowly temperature increases and volume changes are negligible. Then there is suddenly the temperature doesn't change, but volume changes a lot. After some time, both temperature and volume changes. So this is called a P is equal to constant curve. Okay. So this is the point what is called as saturated liquid. This is called a point called a saturated vapor. Most of the book uses a suffix F for this, suffix G for this. Okay. Now suppose if I have a point in between, okay, wet mixture. If I want to know what is the volume of this one, how the volume of this one changes, this is the rule. The volume of a mixture is equal to the 1 minus x into volume of liquid plus x into volume of vapor. Okay. Suppose if this is the specific volume, suppose let us say I have 10 kg. Okay. So then automatically you can multiply the volume of 10 kg of mixture will be mass into the volume of mixture. Suppose if I want to know in this 10 kg how many kgs are steam, how many kgs are liquid, then I can always have mf is equal to 1 minus x into m. The m is the total mixture. mg is equal to x into m. Okay, so that's how the volume of a mixture. The very interesting thing that the volume is directly proportional to the quality. The specific volume is directly proportional to the quality. Not only the specific volume, any other property will be directly proportional to the x. So whenever I have a mixture of liquid and the vapor, their relative properties should be, the resultant property should be proportional to the mass fraction, because a mixture of liquid and vapor always remain as pure. You imagine if I have a mixture of water and steam together, and as long as only these are existing, then obviously they are in the phase. Means if I take one substance and if it is a mixture of liquid of that substance and vapor of substance, there is no other possible pure impurity will occur. It has to be pure in terms of H2O. So that's how I'll calculate the total properties as weighted fractions with respect to the dryness fraction. Next class we will take this one to the next level and try to understand what is the process, then more important are the ultimate culmination of thermodynamics. What for I am learning thermodynamics will come slowly. Okay. Thank you very much.